Welcome, students, to this explainer on systems engineering. Today, we're focusing on a real fundamental truth of our profession, and that is that software never exists in a vacuum. I mean, think about it. A computer only becomes useful when software and hardware are actually integrated. Without hardware, a software system is really just an abstraction, right? It's just a representation of human knowledge. And on the flip side, without software, hardware is just a bunch of inert electronic devices. But together, they form a system. So the overarching theme of today's lecture is that integrating hardware, software, and, crucially, human elements is absolutely essential for modern software engineering. Okay, let's dive right into this. Today, we're covering 1. Introduction to Systems Engineering. 2. Technical versus Sociotechnical Systems. 3. Sociotechnical System Layers. 4. Emergent Properties and Reliability. 5. Non-Determinism and Success Criteria. And finally, 6. A lecture summary and some crucial exam prep. Section 1. Introduction to Systems Engineering. Let's begin by establishing our foundational concepts here. Remember, we aren't just coding in isolation, we're engineering solutions for the real world. To do that, we absolutely must understand systems engineering. We define this as the activity of designing entire systems, taking into account the characteristics of hardware, software, and the human elements of these systems. Now, a very common misconception students have is that systems engineering only applies to hardware, but in reality, as we define it here, it's an incredible interdisciplinary effort. It isn't just about writing code. It includes everything from conceptualizing and procuring components all the way to specifying, developing, deploying, and maintaining the system. A systems engineer literally has to think about the constraints under which the system must be built, the national utilities it relies on, and the diverse ways humans will interact with it over its entire lifespan. Now notice how the lifetime of these large, complex systems breaks down into 4 overlapping stages. Step 1 is conceptual design. This is where we set out the vision, the purpose, and the high-level features in plain, non-technical language. Step 2 is procurement or acquisition, where decisions are made about, say, buying off-the-shelf hardware or software versus hiring contractors to build custom solutions. Step 3 is development, where we actually build and integrate these components. And Step 4 is operation. This is normally the longest phase, where the system is deployed, users are trained, and the system evolves over time. So to do a quick micro-recap of this introduction, systems engineering is the holistic process of designing and guiding a system through these 4 overlapping stages, ensuring hardware, software, and humans all work together smoothly. Moving right along, Section 2, Technical versus Sociotechnical Systems. I want to loudly signpost this for you all right now because this is a crucial exam concept. You must be able to recognize and explain this difference. We divide systems into 2 broad categories. On the left, we have technical systems. These include hardware and software components, but they do not include procedures and processes. For example, a television or a program like Microsoft Word. You see, the word processor I use is entirely unaware that it's being used to write a book. Knowledge of the purpose is simply not part of the technical system. On the right, however, we have sociotechnical systems. These include hardware and software and the people, operational processes, organizational policies, and even external laws. The people in these systems actually understand the overarching purpose of the system. An air traffic control system is a perfect example here. It relies on radar and software, sure, but it also relies heavily on the pilots, the air traffic controllers, and international aviation laws. Remember this critical contrast. Technical systems lack operational processes. Sociotechnical systems are embedded with human purpose and rules. Section 3. Sociotechnical System Layers. Now, to build these incredibly complex systems, we absolutely must understand the organizational environment they operate within, and this brilliantly illustrates the 4 organizational elements that dictate system design. First up, process changes. A new system might mean people actually have to change the way they work, requiring extensive training. Second, jobs. If a system dis-skills a role or causes job losses, you will face massive user resistance. Third, policies. Your proposed system must align with organizational rules, like privacy policies, or it'll just be rejected flat out. And fourth, politics. Introducing a new system can radically change the political power structure in an organization, especially if it shifts who controls access to crucial data. So, for a quick micro-recap, when you design a socio-technical system, you're not just writing code. You are navigating processes, jobs, policies, and internal office politics. Okay, on to Section 4, Emergent Properties and Reliability. Let's shift our focus to why these systems are so notoriously challenging to engineer perfectly. There are three core characteristics of socio-technical systems that create this difficulty, starting with the first one, emergent properties. Now, what does that mean? An emergent property is a characteristic of the system as a whole that only emerges once the system components have been integrated. It does not belong to any individual part. Think of it like a bicycle. The property of being a transportation device only emerges once the wheels, frame, and chain are all put together. In software, system reliability or security are emergent properties. You can't point to a single line of code or a single server and say, yep, this is where the reliability lives. Reliability only exists when the hardware, software, and human operators are all combined and interacting correctly. Let's look at how this builds into real-world scenarios. Tracing the failure propagation diagram here perfectly captures how emergent properties, like reliability, can break down. Let's walk through it step by step using a textbook example of an air conditioning failure. Imagine the AC in a server room fails. That's an environmental failure, right? The hardware gets hot and starts generating spurious, incorrect signals. Then, the software receives these unexpected inputs and behaves unpredictably, perhaps throwing complex error codes. The human operator sees these bizarre errors, gets confused, and begins to feel stressed. And, as we know, people under stress make mistakes. The operator enters a wrong command, overloads the system, and triggers a total system shutdown. The failure propagated from the room's temperature to hardware to software to human panic. This is exactly why you cannot evaluate reliability by only looking at the software in isolation. Section 5. Non-Determinism and Success Criteria. We've covered emergent properties. Now we're going to look at the final two characteristics of socio-technical systems that make them so incredibly difficult to engineer perfectly. But first, I want to pause and ask you a direct question. If we write perfectly logical, bug-free code, why are our socio-technical systems still fundamentally unpredictable? Take a second to really think about that. The code is deterministic, so where does all the chaos come from? Well, the answer lies in human behavior, and this leads us to our second core characteristic, non-determinism. This is the characteristic where a system may not always produce the same output for a specific input. Why? Because people are involved. Human behavior and operational environments constantly change. Think about it. If you give a human operator a task on a Tuesday morning when they're fresh and caffeinated, they might execute it perfectly. But if you give them the exact same task on a Friday afternoon when they're exhausted and stressed, they might make a critical error. Because the emotional and physical state of the human component varies so much, the system's behavior as a whole is inherently unpredictable. And this brings us to the third core characteristic, subjective success criteria. This arises because socio-technical systems tackle what we call wicked problems. A wicked problem is a problem so complex with so many related entities that there really is no definitive specification. Success is entirely subjective. For example, imagine deploying a new medical record system in a hospital. For the hospital management, the system might be a massive success because it generates excellent cost reporting data. But for the doctors on the ground, the system might be a total failure because it requires double the data entry, leaving them with way less time for their patients. To quickly micro-recap these last two traits, socio-technical systems are non-deterministic because human behavior varies, and their success is subjective because different stakeholders have vastly different goals. Section 6. Lecture summary and exam prep. All right, we are wrapping up our explainer for today. So the crucial point is to make sure you can synthesize all of this for your exams. Let's methodically review the most vital facts. Please ensure you can recognize and differentiate these core concepts. Remember, software requires integrated hardware and human elements. You absolutely must be able to contrast a technical system, which lacks human processes, with a socio-technical system, which includes people, policies, and laws. Recall the 4 overlapping stages of a system's lifetime: conceptual design, procurement, development, and operation. And you definitely need to know the 3 traits of socio-technical systems. They possess emergent properties, they exhibit non-determinism, and they have subjective success criteria. Finally, remember how emergent properties like reliability can lead to failure propagation across hardware, software, and human operators. Mastering these concepts prepares you perfectly for our next module, which will delve deeply into conceptual system design. Before we go, I want to leave you with one final provocative question. If we only engineer the code, and we choose to ignore the office politics, the organizational policies, and the realities of human stress, are we actually just building a system that is designed to fail? As software engineers, it is our professional responsibility to realize that if we fail to minimize human and organizational friction, even the most beautiful code will result in a failing system. Thank you so much for your focus today, and I look forward to seeing you in the next lecture.